Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 11, using linear models in a data context. Okay, this is Exercise 1. Old Faithful is a geyser in Yellowstone National Park. The following table offers some rough estimates of the length of an eruption in minutes and the amount of water in gallons in that eruption. The data is consistent with actual eruption and summary statistics that can be found at the following lengths. A. Chang wants to predict the amount of water in an eruption based on the length of the eruption. What should he use as the dependent variable and why? Okay, so if I call this x and I call this y, my dependent variable is y. And it's obvious that the amount of water that will be in the eruption will be based on how long it erupts for. The longer it erupts, the more water that's going to come out of it. So the amount of water is going to be the dependent variable. So the amount of water. And the y part I'm just going to say. He wants to predict the amount of water in an eruption. He doesn't want to predict how long it's going to take to get so many gallons. If we were doing it that way, then we would do that. But he is trying to predict how much water will come out of the eruption. Okay? So you time the eruption, and the amount of water is your outcome. How much water occurred during that period of time. All right, B. Which of the following two scatter plots should Chang use to build his prediction model? Okay, well, let me bring this back up here. So if y is my dependent variable, y is the amount of water, my y axes are here. So if I look at this, this is length, this is amount of water. So I want amount of water to be my y, and I want my length to be my x. Well, this one is reversed. They're saying the amount of water here is my independent variable, and the length is dependent, and we want it the other way around. So it would be this graph here, simply because of what is labeled x and y, or dependent and independent. Part C says, suppose that Chang believes the variables to be linearly related. Use the first and last data points in the table to create a linear prediction model. Okay, so what they're saying here is we want to come up with an equation, y equals mx plus b. So y is my dependent variable, m is my rate of change, x is my dependent variable, and b is my y-intercept. So if it says to use the first and last data points. So if I go back, my first data point is 1.5, 3,700. So 1.5, 3,700. That is my first point. I don't like using commas in, let me do that again. 1.5, 3,700. I don't like to use commas for the thousands because it gets confusing. So there's the first point. The last data point is 4.5, 8,400. 4.5, 4,800. Is that what I said? Let me verify. Yeah, no, 8,400. I reversed that. 8,400. No commas. Okay, 8,400. So this is going to be, let me label these. This is my x from my first point. This is my y from my first point. This is my x from my second point, and this is my y from my second point. And that's where the y2s and x2s come from, and x1s. So now I'm going to come off to the side here, and slope, or rate of change, equals the change in y, y2 minus y1, divided by the change in x, or x2 minus x1. So if I solve this by substitution, y2 is 8,400 minus 3,700 divided by x2, 4.5, minus x1, which is 1.5. And simplifying that, I get 0, 0. 4 minus 7 is 7 with carrying 14 minus 7. 7 minus 3 is 4,700. Divided by 5 minus 5 is 0. 4 minus 1 is 3. Okay, so there is my rate of change, 4,700. And what does that mean? What is my Y? Amount of water in gallons, length in minutes. So for every 3 minutes, 4,700 gallons comes out. That's my rate. Now I'm going to use this equation, and I'm going to finish this problem because it asks for a linear prediction model. So I have a Y, and I have an X, and now I have an M. I just need to find B. So let me write that over here. Y equals mx plus b. Well, I'm going to pick one of these 2 points, and it doesn't matter which one. I'll pick this one because its numbers are smaller. Y is 3,700, so I put that over here, substituting in for y. My m I found over here is 4,700 over 3 times my x from the same point, which is 1.5. Well, that's 1.5 is 1 1/2. And if I make that improper, 2 times 1 is 2 plus 1 is 3. It's also considered 3/2. And that's what I'm going to use here because it will reduce nicely. So there's my equation all set up. The only thing I don't know is my b. So now I simplify. 3,700 equals, these 3's will now cancel. 2 goes into 4 twice. 2 goes into 7 3 times with a remainder of 1. 2 goes into 10 5. And then there's a 0 plus b. See how nice that was, how that canceled? So now I have 2,350 plus b. To get b by itself, I subtract 2,350 from both sides. So when I do that, these cancel. I get b, and this is 0. 7 minus 1 is 6, because I'm going to borrow here. 10 minus 5 is 5. 6 minus 3 is 3, and 3 minus 2 is 1. So there's my b. So my final answer is going to be y equals m, 4,700 over 3, times x, plus my b of 1,350. Okay, so this is the answer, and I like leaving my rate of change as a fraction, but in this case, we're finding out how many gallons in 3 minutes. So I could reduce this, and I'm going to. So it's going to be y equals, well, 3 will go into 4 once with a remainder of 1. 3 will go into 17 5 times with a remainder of 2. 3 goes into 20 6 times. 6 times 3 is 18 with a remainder of 2. And this is just going to keep repeating. So it's 1,566 2/3, okay, or 0.67. 1,566.6 repeating would be 0.7 if we rounded. X plus 1,350. Since it's a prediction, it's okay to round. So now I'm going to focus on this equation because now the rate of change is for every minute, not every 3 minutes. So now it says a friend of Chang's told him that Old Faithful produces about 3,000 gallons of water every minute that it erupts. Does the linear model from part C support what Chang's friend said? Explain. So here's your explanation. You take your equation that you came up with. Okay. And now 3,000 gallons goes over where Y is. That's how much water. And for every minute, that would make my X 1. So 1,566.7 times 1 is 1,566.7 plus that 1,350. So 3,000 should equal what this adds up to. So 7 plus 0.0 is 0.7. 6 plus 0 is 6. 6 plus 5 is 11, carry the 1. 5 plus 3 is 8, plus 1 is 9. And 1 plus 1 is 2. So we're only about 83.3 gallons off, which is pretty close. So I would say yes, this does support what Chang's friend said. It is close to 3,000 gallons per minute. But, let me give that some thought though. That's not true. In the first minute, that would be true. But then for some reason, if it's 3,000 gallons, that would mean that every minute, this would be the same every time. So, well, I don't know. We'll see. I'm thinking that's kind of close. Yeah, so with giving that thought, our rate of change is right here. This is our rate of change. Okay, and that is not 3,000. So the answer is no. So what he was thinking was, he was possibly thinking when I plug this value in for 1 with my y-intercept that we predicted up here, that we get 3,000 gallons every minute. Well, it's actually 1,566.7 gallons per minute. Okay, E, using the linear model from part C, so I'm going to rewrite that again, y equals 1566.7x plus 1,350. Does it make sense to interpret the y-intercept in the context of this problem? And the answer is a big no. And the reason is, does it make sense that when the geyser is not going off, in other words, when we are at 0 minutes, that we get 1,350 gallons that erupt from it? No. Because at 0 minutes, it's not erupting. If it doesn't erupt, no water comes out. So 1,350 does not make sense in the context of this problem. Okay, number 2. The following table gives the times of the gold, silver, and bronze medal winners for the men's 100-meter race in seconds for the past 10 Olympic Games. Okay, so notice in 76, 80, 84, 88, 92, 96, 2000, 2004, 2008, 2012. Okay, so every year it was 4 years apart. There was a time where they did the winter and summer the same year, and then the one year they split them off, it must have been the Winter Olympics that they started 2 years after. So there should have been a 2-year space somewhere. Anyhow, doesn't matter to this problem. Anyway, if you wanted to describe how mean times change over the years, which variable would you use as the independent variable, and which would you use as the dependent variable? Okay, I just had to pause for a really long time and forgot where I left off, and if I'm repeating myself, I apologize, but I'm on number 2A, and it says, if you wanted to describe how mean times change over the years, which variable would you use as the independent variable? And which would you use as the dependent variable? Okay, so which is independent and which is dependent? The year would be independent. So independent would be the year, and dependent would be the mean time. Okay, so it depends on the year what your mean time was. Mean time does not determine year. The year determined the mean time. B, it says to draw a scatter plot to determine if the relationship between the mean time and year appears to be linear. Comment on any trend or pattern that you see in the scatter plot. Okay. I'm going to bring in a grid so I can plot this because they give us nothing. One moment. Okay, so here we have the independent variable year, that's our x-axis, and our mean time in seconds, which is our y-axis. Draw a scatter plot to determine. So if I go up here, 2012 is 9.72, so this is going to be an approximation. So 2012 is 9.72, which would be somewhere around here. Okay, so there's 1 point. We just need to keep going up and doing this. 2008, 9.83. 2008, 9.83 is right about here, so 2008 is right there. 2004, 9.86, so 2004 was just a little smidgen higher, 9.86 maybe right there. Okay, and then after that, 2000 was 9.97, so if I go to 2000, 9.9 here, that's almost 10, so I'd put that like right there. Okay, and keep going. 96 was 9.88. 1996, 9.88, which would be about here. 1992, 10.01. 1992, and just a smidgen above 10, which is about there. All right, so we see a pattern. It looks like there's a pattern here. 1998, 9.96. 1998, 9.96. 1984, 10.13. 1984, 10.13, which would be up here. And 1980, 10.3. 1980, 10.3. And 1976 was 10.9. 10.09, which is 76. 10.09 is just under 10.1. So now I would get my ruler, because it says to draw a scatter plot to determine if the relationship between the mean time and years appears to be linear. So if I get my ruler out and I bring that down here and draw a line of fit, an approximation, then we are going to, I would say it would be something like this, and then I'd draw the line through it like that, and then I would assess this. And it looks okay right there, but I might want to rotate that a little because some of my data is off. So I want to have a line that would probably, there, that looks pretty good right there. So if I move that up, a lot of the points are right on the line. Okay, and then we have a few points off the line, 3 below, 3 above. So I would say that's a pretty good line of best fit right there. So it says, comment on any trend or pattern you see in these scatter plots. So what I would say is, there appears to be a pattern. It looks linear. And as the years increase, as the time goes by, the mean time in seconds decreases. Okay, so what does that mean? No pun intended there. Mean time, well, what is this? 100-meter race. So if it's taking less time for runners to do it, it means that humans are getting faster. As the years go by, they're getting faster and faster and faster. They're getting it done sooner, so they're finishing the race quicker, so they're obviously way faster. There's a big difference between 10.3 and 9.7 in the grand scheme of things. Okay, so there we go. C says one reasonable line goes through 1992 and 2004. So if I go back, 1992 is right here, 92 is here, and 2004 is right there. And it goes right through those 2 points. So find the equation of that line. So what they're telling us is we have an X and a Y. And 1992 is the year. That is our X. 2004 is our year. That is our X. Our Y is our time in those years. So in 1992, which is right here, it is 10.01, and 94, was it? No, it wasn't 94. 1992 was 10.01. 1992 was 10.01, and 2004 was my other time. So 2004 is here, and it's 9.86. So that's going to be 9.86. So there are my 2 points that they're asking us to do a line of fit. Okay, so what I'm going to do is, I'm going to say the slope, we're going to find the slope, or the rate of change, which is, this is x1, and this is y1, and this is x2, and this is y2. Let me change color here. So we take y2 minus y1 divided by x2 minus x1. So my slope is going to equal y2, 9.86, minus y1, 10.01, and then 2004 minus 1992. Okay, and we're going to simplify that. 9.86 minus 10.01 is... Okay, so rather than just bringing up the calculator here, I'm just going to calculate it here. So 9.86 minus 10.01 comes out to be negative 0.15. And 2004 minus 1992 is 12. Okay, so now negative 0.15 divided by 12 comes out to be negative 0.0125. So that is our slope. So now we take y equals mx plus b. We just found m, and we have an x and we have a y. I will use the 1992 and the 10.01, so my y is right here. So that's going to be 10.01 equals my slope, which is negative 0.0125. Times x, which is 1992, plus b. So 10.01 equals, and 1992 times negative 0.0125 comes out to be negative 24.9 plus b. So when I add 24.9 to both sides, I get b equals 1943. So it's 34.91. Now I write my equation, y equals m negative 0.0125x plus 34.91. And that is my line of best fit equation. B says, before he saw these data, Chang guessed that the mean time of the 3 Olympic medal winners decreased by about 0.05 seconds from one Olympic game to the next. Does the prediction model you found in part C support that guess? Okay, well, our change is right here. So 0.05, this is 0.0125. So I would say no, it does not support, because 0.05 is a far cry from 0.01. Okay, so you want to be closer than that. 1/100th is quite a ways away from 5/100ths. It's a big difference. Okay, I kind of pause there because whenever I think about something and it doesn't seem right, I have to check again. We have to keep in mind what this is, okay? Our equation is based on years. And how many years is it from one Olympics to the next? Well, it's 4 years, and our years is our y. So for every time it changes 4 years, I'd have to take this, and I would have to say negative 0.0125 times 4. 5 times 4 is 20. 4 times 2 is 8, plus 2 is 10. 4 times 1 is 4, plus 1 is 5. And look at what this comes out to be. Negative 0.05. So now that I think about this more, that is a good prediction. Because remember that y is years, and Olympics are every 4 years, so you have to multiply this rate of change by 4, because Olympics don't happen every year. Okay. E, if the trend continues, what mean race time would you predict for the gold, silver, bronze medal winners in 2016 Olympic Games? Okay, so we use our equation, y equals negative 0.0125x plus 34.91. And the last Olympic, 2016 is the year, so what we would do is solve this for x. So I would say 2016 is my y, equals negative 0.0125x plus 34.91. Subtract 34.91 from both sides. and I get negative 0.0125x equals 2016 minus 34.91. I'm just using a calculator to save time. 1981.09. And then I divide by negative 0.0125. Divide by negative 0.0125. These would cancel, leaving me with x equals whatever this comes out to be. So I divide that by negative 0.0125, and I get negative okay, I got a real wacky number there, and whenever that happens, obviously I have to check it, and because things have to make sense in our world, because we don't just do a problem and say, okay, I got an answer, I'm going to stop now. I made a mistake here. Y, let me go back here. Y is our mean time. X was our year. So when we graphed it, X is year, Y is mean time. So I apologize for doing that, making that mistake, but I will fix it now. So I'm trying to find our mean time, which is Y, which is negative 0.0125. X is my year, 2016, plus 34.91. Okay, so Y is going to equal, so it's negative 0.0125 times 2016, which is negative 25.2, plus 34.91. So my Y, which is my mean time, is going to come out to be 9.71. So if I go back to my graph, 9.71 for 2016 would be right over here somewhere. So that does make sense. Okay. F, the data point 1980, 10.3 appears to have an unusually high value for the mean race time of 10.3. Using your library of or the internet, see if you can find a possible explanation for why that might have happened. Okay, I'm not going to do that problem. And that will be the end of lesson 11. So review the lesson summary and go do your problem set.